Okay, hello. Apologize for having to miss class. I hope to be back in the saddle on Friday. What I'm going to do is I want to start toward the, I promised to show you what happens with certain linear systems where you have vector x, derivative of vector x is equal to a times uh, vector x. And I have the notes already up here, so let's just go to share screen. So you during this lesson here, I have the notes that I'll put a link to. And what I think I'll do is I'll do this in two quick things. I'm going to do something involving node, and I'll be giving what's known as a nodal source, and I'll explain what I mean by that. And then I'll also be doing what's known as a nodal saddle. And again, I have the notes and some stuff up here, and I'll put a link to this in our course Sakai page. So let's go ahead and get started. Let's see here, get rid of this. It's always in the most inconvenient part. And let's get started with an example. And I'm going to, well, let's see right here, get this started. And I'm going to be using the little, my tablet to write on. Now, in this particular case right here, we're going to start with the differential equation x bar prime is equal to a x, where a is a following matrix. And I want to make sure I get it right. -1, 6, 6, and -3, 8. Now we know the solution will depend on the eigenvalues and eigenvectors. And so let's find the eigenvalues. So if I take a minus lambda I, now I used m in the notes just because lambda is a pain in the neck to then you take the determinant of this, what you get is you get the characteristic equation. 1 minus lambda, that's a lambda, 8 minus lambda, plus 18. And you set this equal to 0 to find the eigenvalues. And what you find if you do this carefully is that's a lambda squared plus 8, let's see, minus 8 lambda plus 1, so it's -7 plus 8. Let's see here. That's a minus there. So let's get rid of this. It's not a plus. Have to erase. A lot easier to do with a chalkboard. Or it's going to be here. It's going to be, shoot. Let's get down here. So -8 plus 10 is 0. And we get that lambda squared -7 lambda. That's 18 here. And then that turns out to be plus 10. This clearly factors, as you can see right here. So we'll move up to the top. So this certainly factors as lambda -5, lambda -2. So the eigenvalues are lambda equals 5, lambda equals 2. Now, what we get out of that is if we do lambda equal, and I'll just separate these two. Now, taking away lambda minus 5, what I end up getting here, you put in a 5 here, you get a minus 6, a 6, a minus 3, and a 3. So it's easy to see that the eigenvector, or an eigenvector, would be a 1, 1. Taking away 2 from this, we get a minus 3, 6, minus 3, 6. So it's clear that an eigenvector here would be 2 and 1. So all solutions look like C1, 1, 1, e to the 5t plus C2, 2, 1, e to the 2t. So all solutions basically look like this, okay? No, I don't care where I save that. Let's cancel that. I'll save it some other time. So I'll make this a little bigger now. This is our whiteboard. All right, so now, what does this mean? Well, what this means here is that if you want to look at all solutions, the solutions kind of look like this. That is C1 e to the 5t plus 2 C2 e to the 2t, or the second one is C1 e to the 5t plus C2 e to the 2t, or you can write them like this. Your x of t is going to be C1 e to the 5t plus 2 C2 e to the 2t, and your y of t looks like this. Now, what this tells us is that our solutions are going to come in these pairs. And you can see this right here, if you think about it, one way to think about this is a parametric curve. In two space, where you have a formula for the x and a formula for the y. So what we can basically do is we can actually plot these for various initial conditions. And so let's go ahead and do that. Let's go ahead and plot one. And let's look at the first case. Suppose we have the initial condition, x of 0 is 0 and y of 0. I didn't want 0. I wanted a 1 here. So I think I'll just rub that out, put a 1 there. Okay. Well, then this enables us to solve for our initial conditions. So if I just write a 1 is equal to, plugging in 0 here, we get C1 plus 2C2. The second one says 1 is equal to C1 plus C2. And it's pretty easy to see that this is satisfied when C1 is 1 and C2 is 0. Now you can do some algebra to do that, But what this gives us the following equation. X is equal to e to the 5t. Y is equal to e to the 5t. And what this actually is, if you think about it, x and y are the same, which is what's known as a line, but it's a half line. Because e to the 5t is always greater than 0. So let's take a look here. Let's take a look at this. And if you try to plot this parametrically, it's really kind of simple. This is the e to the 5t. And this is the e to the 5t. And then remember though, your t can actually go to negative numbers. So let's make that a good, very close to 0. And we can see that solution right here. And basically, we started our initial point, and as t goes to negative infinity, asymptotically, these two things go to 0. So as t runs to negative infinity, we're going along that line. As t runs positive, we're going along the line this way. And this is what we say that 0, this point that this never quite reaches, is called a source. And the arrows on this particular curve run the other way. So that's a nice little line right there. Now let's go back to here. And let's move down. Extend this a little bit. And this will be our whiteboard that we never erase. And let's go back here. So now let's look at a different sort of situation. Let's now look at, let's say we had an initial condition instead of, so let's do this initial condition here. Suppose instead we had x of 0 is 1, y of 0 is negative 1. Well, let's remember, in case we already forgot, this is what we're plugging into, right? Well, we're going to solve for the C1 and C2. So if we go down to this initial condition here, what we have 1 is equal to C1 minus 2C2. And then we also have negative 1 is equal to C1 plus C2. What I like to do here is I like to go ahead and subtract. What I can do is I can subtract these two. So 1 minus a minus 1, I want to make sure. 1 minus, so I subtract this equation from this equation. That cancels the c's. So it gives me a 2 is equal to minus 2c2 minus, let's see, it's right here. That's negative 1. And let's see here. Ooh, this is not a minus, darn it. That's a plus. That's my bad. So what I have now, that's going to be 2 is equal to C2, because 2 minus 1 is 1. So C2 is equal to 2, and that means C1 has to equal negative 3. So our solution here looks like this, C1 and C2. So we have minus 3 e to the 5t times 1, plus 2 e to the 2t, 1. So this leads to x is equal to minus 3e to the 5t plus 4e to the 2t, and your y is equal to minus 3e to the 5t plus 2e to the 2t. Now, what the heck does that look like? Well, we go on to Desmos here. Let's take a look at this equation. We have minus 3e to the 5t plus 4e to the, make sure this is right, 4e to the 2t minus 3e to the 5t plus 2e to the 2t. Now, this thing here, this is a 0, 0, where t equals 0. If we let this go, say, to minus 10 to maybe 2, look at that. Look at these. The characteristic here is sort of flares up like this and moves around like that. So this is a second kind of solution we get. Now, on the course notes, that I have up there, I put in more solutions than just this. But this is typical of a nodal source. The thing starts out here at 0, the source, bounds up and curves around like that, okay? And I think I'll do one more on this example, and then we'll move to a saddle point. Okay, so go back. So let's do one more, and there's another one on the notes that I didn't do. I just don't want to be too redundant. But let's say now, suppose we start with x of 0 is minus 2, and y with t equals 0 is going to be 0. Then we get the following equations. Minus 2 is equal to c1 plus 2c2, and 0 is equal to c1 plus c2. And solving these two right here, it's you can do it a bunch of ways, but if you do the old subtraction method, take this away, we get minus 2 minus 0 is equal to c2, and c1 is equal to 2. So our things are going to be 2e to the 5t minus 2, 2, 1. I'll just write this on the other side. It doesn't really matter. Or x is equal to 2e to the 5t minus 4e to the 2t, and y is equal to 2e to the 5t minus 2e to the 2t. Okay? Now let's go ahead and let's take a look at what this looks like in Desmos. We have 2e to the 5t minus 4e to the 2t, and then 2e to the 5t minus 2e to the 2t. And then in order to get this, notice that's at t equals 0. So let's go to minus 10, see what happens. And sure enough, we're emanating from 0, but we come right down and you get this other characteristic as you see right here. I think that's kind of interesting. So that gives you an idea about a nodal source. Now, a nodal sink, now I'll just want to say this, that's a source. And I'll just write this right here. A sink, it's not here, occurs if the eigenvalues are both negative. And basically what you do is you just, the type of curves are kind of the same. It's just that you're reversing the arrows. That's really it. So I'll let you, think about the sinks on your own. What I'd like to do now is I'd like to go ahead and go to a saddle point. So let's talk about saddles. This is a case where the eigenvalues have opposite sign. And I have one of these also done for you. So I'll just extend this. And the example I have worked out here, and I'll go ahead and just, and I have some of the notes that are typeset, but the example I have worked out here is A is equal to 1, 4, 2, minus 1. Actually, let me just take a quick break because I forgot I didn't do everything I wanted to do with a node. As far as getting a pretty pictures, let's forget what I said about this, and let's go back to the source, and let's go to a phase plane plotter. Now this one you do have a link to, and you have to be a little bit careful here. When you input this stuff, the inputs are a little bit tricky in the sense that it's kind of fussy how you enter it. Now remember what the A was. A was minus 1, 6, minus 3, 8. So the way you input this is going to be minus x plus 6 times y. And you have to put a little star there. It gets upset if you don't. And then the next one is minus 3 times x plus 8 times y. And let's graph the phase plane. And you can see these arrows, and these arrows would indicate the source. Now, your half-line solution kind of looks like this. We have this something like this, and we have something like that. So you can see the typical solutions that we have. We have one like this. Now they kind of meet at 0, but 0's out at t equals infinity. Okay? And you have this and you have that. And the arrows indicate the fact that we're moving away from the origin, like that. So this is a clear source, nodal source. Okay? Now let's go back to a saddle. And the saddle is going to look something like this. Let's go back to my saddle here. Now, I'm going to just, running a little short on time, but if you compute A minus lambda I, what you get is 1 minus lambda, 4, 2, minus 1 minus lambda. And I'm going to spare you the algebra, but if you take the determinant and you work it out very carefully, what you end up with is you end up with lambda squared minus 9. And I'll leave the details to you. So those are going to be the two eigenvalues. So let's go ahead now and let's look at the eigenvalue of 3. Well, if you plug in 3 here, you get a minus 2, 4, 2, minus 4. So a good eigenvalue here would be 2 and 1. For minus 3, 1 minus a minus 3 is a 4. Minus 1 minus a minus 3 is a positive 2. So you end up with a second, let's see here. This is at my saddle here. So you end up with 1, negative 1. So your solutions look like C1 e to the 3t, 2, 1, and C2 e to the minus 3t, 1, and negative 1. And you could actually, again, you can solve these for various values of C. And I went ahead and worked it out with very much the same algebra. So doing that, again, this is a saddle. Let's go ahead and look at the kind of solutions you would get out of here. For example, let's say you had x0 was equal to 3 and y0 was equal to 0. Well, then the solutions you would basically get, and I kind of picked this out right here, your x would be 2 e to the 3t plus e to the minus 3t, and your y would be e to the 3t minus e to the minus 3t. That's kind of a nice little setup here. But let's just go ahead and take a look at what that looks like. That's 2, 1, 1. So let's plot that with Desmos, see what kind of thing we get there. So let's go ahead and get rid of this. And 2 e to the 3t plus e to the minus 3t. And the next one would be e to the 3t Oh, that's not what I want. Come on, I don't want that. And we get this beautiful hyperbolic shape right here. And this kind of looks like the hyperbolic trig functions, doesn't it? Kind of looks like that beautiful hyperbolic shape. Now, if we wanted to instead, let's say we wanted to have the, let's go back to our paint here. That was a nice little solution. What happens instead is, suppose we wanted to have, let's say x of 0 equals 0 and y of 0 equals, let's say, 3. Then what we'd end up with is we'd have 2c1 plus c2 is 0. And then we'd have c1 minus C2 is 3. Adding together, we would get 3C1 is equal to 3. So C1 is 1. C2 is -2. So then our x would be, in this case, it would be e to the 3t minus 2 e to the I'm sorry, 2, I forgot about the 2, e to the minus 3t, and our y would be e to the 3t minus 2. Okay, it's a minus 1, so it'd be a plus 2. Yeah, you see right here, that's a -1. So -1 times a -2 is a +2. So we would get our situation here. And let's take a look at this. Oh, shoot, I already forgot that. So let's see, it's, okay, it's going to be 2 minus 2, 1 and 2. Okay, 2 minus 2. And then we would get e to the 3t. Oops. Plus 2 e to the minus 3t. And notice this part right here, I'm going to let that go to -10. And we can see we get that part, that sort of hyperbola kind of action right there. Now, this is just graphing a couple of solutions, and I have more of the solutions here. Let's just take a look at the phase plane, and then we'll call it a day. The phase plane here, remember, it's going to be x plus 4 times y. You have to be careful. Don't add an extra space, or else it will not like that. And this is 2 times x minus y. Let's graph the phase plane. And we can see right here, there's your hyperbolic solutions, like so. And as we get close to the node, we can see that how it goes. It comes in and comes out. So part of the way it's moving toward the origin, and part it's moving away. And we can probably make this closer and closer to the node there. But we never quite get there, right? So that's what a saddle point looks like. So this is called a saddle, and that occurs when the eigenvalues have different signs. They're real distinct and different signs. Okay, so I'll stop the share, and thanks for hanging in.